Okay, we have now learned all of the raw theory that we need to learn about acids and bases to finally start getting into how it all relates to analytical chemistry. And that brings us to... Whoops. Sunshine, lollipops, and rainbows, everything that's... Much better. Now, admittedly, a titration is not the most entertaining thing to do in a lab, but it is an effective, simple way to answer two of our major questions in analytical chemistry, which again are, what do we have and how much of it do we have? And so first I'm going to walk you through the theory behind the titration, and then we'll see how we can use it to answer those questions. So let's start by defining a titration. Titration. Adding a standard solution, which is what we call the titrant. Adding a standard solution, what we call the titrant, to an analyte. And to define some terms, standard solution is a species of known concentration. Species of known concentration. And in parentheses, we'll also write and identity. In other words, we know everything about it. We know what it is, we know how much of it we have. And the analyte is the species that we are interested in. Species we are interested in. And maybe we're interested in its identity, its concentration, or both, but something is unknown about the species that we want to determine. And to learn about something unknown, we must always reference to something completely known. Now, there are numerous titrations out there, but we're going to learn about an acid-base titration, starting with a strong acid titrated by a strong base, and then moving on to a weak acid titrated by a strong base. And there's a fair amount of information here. So if you're taking notes in like a classic spiral notebook or something like this, I recommend just giving yourself 2 fresh sheets of paper so that you can see all of the information at the same time. We probably won't need 2 full sheets, but we will need more than 1. So just use the top half of your left page just for drawing this thing called the titration curve that we're going to be working on and writing down the background information, and you'll use the remaining space for notes. And if you're using a tablet, well, you'll just be doing some scrolling back and forth. So let's get started. Strong acid and strong base. And our goal is going to be to construct a graph known as a titration curve, which shows how the pH changes as we add more and more titrant. In this case, the strong base will be our titrant. Let's start by just drawing some crude axes for this titration curve, where our y-axis will be pH, and we'll measure how that changes as we add greater volumes of base. And for the pH axes, we want 12 tick marks, and we want to do our best to evenly space them out, but not kill ourselves. So the way I recommend doing this is first just draw a tick mark at the very top, and then do your best to estimate where the midpoint is, and draw another tick mark, and then cut those 2 sections in half, and then cut those 4 sections into thirds. And if you do it like this, you'll have a pretty decent set of 12 tick marks, relatively evenly spaced. And we will start with a value of 2, and each of these marks represents an increase of 1. Let's just label every other mark. 2, 4, 6, 8, 10, 12, and so our last one will actually be 13. For the volume, it's easier. We're just going to have 4 marks. So once again, start at the very end of the axis, then cut in half, and then cut each section in half. And there's our 4 pretty evenly spaced markings. And each of them should correspond to 25 milliliters, but let's have some accuracy and say that's actually 25.0 milliliters, 50.0, 75.0, and 100 would be the last one. And let's note that the units of volume are milliliters. And now let's get some background information. Our analyte will be a strong acid. I could pick any strong acid I want. Let's just do HI instead of this standard HCl. And let's say that we have 0.0500 molar of this solution. 0.0500 molar of this solution, and our volume is 100.0 milliliters. Quickly pause the video and ask yourself, what is weird about this situation? The answer is the analyte is what we're supposed to be interested in, and yet I seem to know everything about it, its identity and its concentration. Again, in real life, we would not know at least one of these things, otherwise what would be the point of the experiment? But right now we're not talking about real life, we're learning about the theory behind the titration. So we're going to start with the situation where we know everything, and then learn how we can build a titration curve from that information. Even though in real life we would generate the titration curve using an instrument called a pH probe, and then use the theory that we're about to learn to figure out how that titration curve lets us know this information here. And so our titrant is going to be, let's go with the classic strong base, NaOH. But I can pick any strong base I want, and the theory will be exactly the same. And we'll say that this titrant's concentration is 0.100 moles per liter. Now the reaction that is going to occur is a neutralization reaction. Acid meets base. They neutralize. The only important species are the protons from the acid and the hydroxide from the base. Because we know that since they're both strong, they will 100% dissociate in water into protons and hydroxide ions respectively, and what's left behind are going to be ineffective conjugate acids and bases, or what you would call a spectator ion in Gen Chem. So these will react to completion, forming water. Now the first thing I'm going to do, I'm going to label step 0. Before we even touch the titration curve itself, I want to determine this very important point called the equivalence point. So step 0, calculate equivalence point. Sometimes we'll call it the equivalence volume, in which case the abbreviation is V subscript E. Now the equivalence point is defined as where the moles of our acid, HI, are equal to the moles of the base, NaOH. But to make our lives a little bit easier as we go through the math behind all the various points in this titration curve, we're going to change our prefix and think in terms of millimoles. So we'll redefine it as when millimoles of HI equal millimoles of NaOH. And the reason we're thinking about millimoles is because our volume is in terms of milliliters, and yet concentrations, like molarity, tend to be thought of in terms of moles per liter, and I don't want to have to keep converting from milliliters to liters. So we're going to say that a unit of molarity can also equal a millimole per milliliter. If 1 molar equals 1 mole per liter, well, that means it also equals 1,000 millimoles per 1,000 milliliters. Or we could just say 1 millimole per milliliter. And that's going to allow us to not have to do all sorts of converting back and forth, as I'll show you momentarily. So let's calculate the equivalence point. So What do we know? Well, we know the concentration of HI is 0.0500 moles per liter, or using our new definition, millimoles per milliliter. We know the volume of that HI is 100.0 milliliters. And on the other side, we know that our concentration of sodium hydroxide is 0.100 millimoles per milliliter. And we are trying to figure out what volume of that base do we need to add so that the two quantities are equal to each other. And we can see that our units will work out so that milliliters cancels, we'll be left with millimoles on the left side, and if we do our algebra correctly, we will end with VE equals 50.0 milliliters.
Wait, Dr. Geller, isn't that just M1V1 equals M2V2?
No, it is not, although that is a very common misconception. But M1V1 equals M2V2 is really for dilutions, not figuring out equivalence points, even though mathematically they look like they're the same formula. But they are completely different conceptually, to the point that if you were to write M1V1 equals M2V2 down on an exam for calculating the equivalence point, I would take half credit off.
Harsh much?
No, because again, it is chemically and conceptually wrong. But I know it's not intuitive, so let's get into why. Now we'll use a visual to hopefully hammer out the differences between these two formulas, starting with the dilution formula. So let's say that we have a 3-liter solution containing 6 moles of acid, thus we have 2 moles per liter. Usually we would just have concentration and volume information, and by multiplying the two together, we could determine how many moles there were in solution. Now let's say that I add 1 liter of solvent, and only solvent, to this solution here. Well, now there's more solvent for these 6 moles of acid to swim in, so they spread out more on average, they become more dispersed, the concentration goes down because our volume has gone up to 4 liters. But we still have 6 moles of acid. And so when we first covered the dilution formula in this class, I showed you this kind of triangular equality. And that's why this formula works, because the moles haven't changed at all. It's just that the concentration has gone down because the volume has gone up. And so these two wind up being equal as well. Now let's contrast that with the equivalence point situation. Here we have the same starting acid solution, 6 moles and 3 liters, 2 moles per liter. But let's say our 1 liter that we're adding to it isn't just solvent, but it's 6 moles of base in some solvent. In other words, we have 6 moles per liter of that base. And so we have equal moles or amounts of the acid and base, which when thinking in terms of concentrations and volumes, can be expressed as the molarity times the volume of the acid is equal to the molarity times the volume of the base. But chemically, what's going on here is completely different than in the dilution. Let's see it with a visual. We add the two together, the moles of acid and base meet and annihilate each other. We now have a 4-liter solution, but we don't have any of either species remaining. If we were to fill out our reaction table, we would say initially we had 6 moles of both, then they went down to 0. So even though the two equations are mathematically identical, conceptually they are completely different. And that's why way back in lecture 2, when we first covered the dilution formula's logic, I told you that it was important to understand that logic for this moment here. We're not actually causing any real reaction. We're just dispersing the chemicals that give it the brown color, having them spread throughout this solution. And this is going to be a very important point for later in the semester when we talk about the difference between a dilution and the equivalence point. So does that make sense, rando student off the street?
Yes, Dr. Geller. In fact, I think I speak for all of the students when I say that it's perfectly reasonable to take off points for not understanding the difference.
Okay, great. So the next step is to actually talk about the titration itself.